Hello, welcome to our Deep Learning Final Competition presentation. Our team consists of Schwan, Buzz, Steven, and we are Group 25. The task at hand is straightforward, predicting the positions of simple objects in motion at frame 22 based on the first 11 video frames. To tackle this challenge, we divided it into two distinct parts, each addressed by its own model. Firstly, concerning the generation of accurate masks for the ball's position from an image, we opted for the implementation of U-Net. U-Net, a state-of-the-art convolutional neural network, initially designed for medical image segmentation by Ronaberger and colleagues in 2015, was chosen for its efficacy. Secondly, in predicting the final position of the ball from a time series of ball mask frames, we implemented both neural ordinary differential equation, ODE-based, and convolutional LSTM models. The left panel of the accompanying figure illustrates the graphical representation of the image segmentation model responsible for producing masks for the first 11 frames. Conversely, the right panel depicts the frame prediction model, which yields the final output classification. To investigate the initial task of generating a ball position mask from a given input image, we employed the U-Net architecture proposed by Ronaberger and colleagues. The U-Net model is designed to accomplish data-efficient image segmentation through robust image augmentation. This is achieved by adopting a U-shaped architecture comprising a contracting encoder path and an expanding decoder path. The encoder path functions akin to a convolutional neural network featuring repeated convolutional and pooling layers for learning abstract feature representations. On the other hand, the decoder path incorporates upsampling and concatenation operations to recover spatial information lost during the contraction phase. The inclusion of skip connections between corresponding layers in the encoder and decoder paths facilitates the transfer of high-resolution features, contributing to precise localization. For the first part of the problem, we trained our U-Net model on the images and masks provided by the labeled training set. In the figure on the right, we have a comparison between the predicted masks, bottom right panel, versus ground truth, top right panel, and we can see that our trained model has great performance. You can see how it compares to the original input image. In particular, it achieved a validation IOU of 0.9398 on the Haldol validation set, which we consider to be quite impressive. To address the second part of our problem, predicting the final position of a ball based on masks of its locations in the first 11 frames, we adopted the convolutional LSTM architecture proposed by Shi and colleagues in 2015. This model seeks to combine the spatial learning components of convolutional neural networks with the temporal learning features of LSTM models. In conv-LSTM, convolutional operations are applied to both input data and the hidden states of LSTM units, facilitating the model and capturing spatial patterns while retaining memory of preceding sequences. The utilization of this dual architecture renders conv-LSTM models well suited for acquiring temporal structures within repetitive images or videos, thereby justifying our selection for the current investigative task. The convolutional LSTM is implemented for a 49 class classification task. Within the labeled training set, each video undergoes the selection of 12 consecutive frames, with the initial 11 frames serving as input to the conv-LSTM and the 12th frame designated as the ground truth. A comparison between the model's prediction for the 12th frame and the actual frame allows for the calculation of loss and subsequent backpropagation. The intersection over union, which is IOU, for the next frame validation is 0.7063, and for the 22nd frame it is 0.2017. As illustrated in the figure on the right, the model exhibits the capability to capture certain movement patterns, yet struggles to maintain accurate object shape. In the figure at the bottom, we have a schematic representation of the prediction pipeline employed for this part of the problem. From our results, we were able to draw two main conclusions. Firstly, that the U-Net model performs excellently on the image masking task. Secondly, though the conv-LSTM is an interesting method, we were unable to get really good results with it. A few possible limitations for the model's poor performance could be using a convolutional LSTM model. We are framing the problem as a 49 class prediction task where there are only 3 to 7 object image. Further, it is likely that the error could have been accumulated through our use of SSL. Finally, though it is possible that additional model training on unlabeled data could have helped, it does not seem that the lack of training data is our main problem. Though we ultimately decided to use convolutional LSTM, we came to the solution fairly early on and thus implemented 2 additional architectures to try to overcome the aforementioned issues. The first of these methods frames the problem as predicting the likelihood that each pixel in the final frame contains the ball, reducing the problem to a binary classification task. After only 5 training epochs, this model was able to achieve an IOU of 0.2001 compared to the 50 epochs it took to train the 49 class model to achieve an IOU of slightly better at 0.2017. Despite these promising results, it is worth noting that framing the problem as a binary task limits the model's ability to predict collisions. We assert that given more training time, this approach may have outperformed our current model. The second method we tried was neural ODE models, as proposed by Chen et al., as opposed to traditional models which have a pre-specified set of hidden layers, learning the evolution of the system over time through the solving of differential equations. Further, as these models are able to work in continuous time, they are well suited for predicting the evolution of physical systems. It's worth noting, however, that these require rigorous hyperparameter tuning and computation due to the use of ODE solvers, and thus infeasible given our time and resource constraints.